This is a GCSE physics presentation looking at the uses of the generator effect in terms of alternators and dynamos. To get started, a student is moving a wire up and down through a magnetic field. Do you agree or disagree with the student's statement that moving the wire up and down will generate an induced current? Pause the presentation, spend 2 minutes, come up with an answer, and then restart whenever you're ready. Well, the fact is that moving that wire up and down through that magnet will cut through magnetic field lines, and therefore we will induce a potential difference. However, there is no complete circuit visible, and if there's no complete circuit, then there will be no induced current. If the circuit was complete, then yes, we would indeed get an induced current because of the induced potential difference. In this lesson, we're going to look at how alternating current is generated using an alternator, and then how we can generate direct current using the dynamo. And when it comes to producing AC alternating current or DC direct current, there are two different machines that can be used, but they all come along the same concept of we need to get a wire rotating inside a magnetic field. There are subtle differences though. If you look at the pictures on the right hand side, there should be one obvious difference straight away, and that comes to the little orange bits at the bottom, and we're going to look at those structures. When we have our alternator, we have our coil of wire rotating around. Now if you look, this is very similar to the structure, the format that you would get in terms of the motor effect, and very similar to the structure and format you get when looking at a dynamo. However, the subtle difference is if you look at the bottom of the diagram, we do not have a split ring commutator. What we have is two separate slip rings, and the two separate slip rings mean that the blue wire and the pink end of the wire or coil are always connected to that particular slip ring. So if you look, the blue side is slightly shorter, is connected to the first of the two, the larger of the two slip rings, and the smaller slip ring has the pink side of the coil going down and making contact with it. Remember that there are brushes, normally carbon brushes, making contact with the slip rings, or a split ring commutator in other examples. So what we've got here is we've simply got two kind of snapshots of the rotating coil, and we're going to have a look using the Fleming's left-hand rule to see what's going on. I've also color coded each of the slip rings so you can match the slip ring with the relative side of the coil that it's attached to blue and pink to pink. Now if you look at the left picture, you can see that the pink is on the left hand side of the coil and the blue is on the right hand side of the coil. If you use your left hand rule, remember your magnetic field line was going from left to right, north to south. The movement on that particular part of the coil was going upwards, so your thumb should be pointing upwards, which means that your second finger should be pointing towards you, which is the direction of current along the pink. That means that the current will travel along the pink, down the long arm of the green, and out the pink slip ring. When on the blue side, you have the opposite, of course, and hence the current will be pointing away from you towards your screen. When we rotate round, normally you'd be used to a split ring commutator, making sure that the current is always flowing in the same direction. However, the slip rings mean that the current is not flipped over, and as a consequence, the current flowing through the pink side of the wire is now traveling in the opposite direction when you move on to the picture on the right, and we've rotated the coil 180 degrees. What that means is previously where at the pink slip ring the current was flowing away and out, it's now flowing into the pink slip ring. And the reverse is also true with the blue, where previously the current was flowing into the blue side of the coil, it's now flowing out of the coil. And every half turn, when you get to that vertical point, you will flip the direction of the current. When we go to DC, you can see that we have got rid of our slip ring and we now have brought back in the split ring commutator. What that means is that the current is always flowing in one direction, just as it is in the motor effect. However, unlike the motor effect, there is no current being supplied to the wire. The only current in the wire is resulting from the induced potential difference as the wire cuts through the magnetic field lines. There is no power supply, there is no battery, and this is the one you need to be careful of because it's so easy to get this confused with the motor effect diagram. In the motor effect, we have to supply the wire with an electrical current, the loop with electrical current. In a dynamo, there is no supply of electrical current to the wire, but we do have to get some way of making that coil rotate. If the coil is not rotating, it's not going to cut through the magnetic field line, and if it doesn't disrupt the magnetic field, then we will not have an induced potential difference. And remember, if we don't have a complete circuit, we will not get an induced current even if we do have that induced potential difference. Remember, your split ring commutator ensures that only one side of the loop is touching one wire at any one time, and it means that no matter which bit of the loop is on the right or which bit of the loop is on the left in terms of being inside the magnet, the flow of current is always the same way. It does not work the same as slip rings, and remember, slip rings mean that current travels in one direction and then reverses, which is where we get our AC from. The split ring commutator inside the dynamo means we have direct current. And again, you can see how the split ring commutator ensures that each side of the split ring is only touching one positive or negative terminal, and it means that we always have a positive and negative terminal. The positive will always be on the right and the negative will always be on the left, regardless of how much the loop rotates. And we do have a fraction of an instance where we have to rely on momentum, which is the third picture along the bottom, where the split ring commutator is not making contact with either of the brushes on the wires. So to finish off, make a list of the different ways that you can identify a diagram as being linked to either the motor effect, being linked to the alternator, or being linked to the dynamo. Pause the presentation, spend 5 minutes, come up with the best answer you can, and then you can check to see how you've got on. Pause now. Well, there's a number of different things you can look for. In terms of the motor effect, we must have a current supplied. The outcome is the rotation of the wire, so that is what we want out. We want that thing to move. The current does not change direction. It's always going in the same direction, and there's a split ring commutator involved. In terms of alternators, we have no power supply to provide a current in the wire. The loop must be rotated by some method. For example, it must be a wind turbine or wave machine or something that gives that rotation motion. We also have current changing direction in the loop. It goes one way around the circuit and then rotates and goes the other way and reverses and goes the other way. And what we have is we have slip rings instead of a split ring commutator. And last, of course, the dynamo. Again, just like the alternator, there's no power supply to it for the current. Just like in the alternator, the loop must be rotated using some other method. For example, in a dynamo, it can often be a little wind-up crank that you just simply do by hand. In a dynamo, the current does not change direction. It does not reverse in that loop or coil. It is only in one direction, hence we get DC electricity, and it does require a split ring commutator rather than slip rings.